Bismillahirrahmanirrahim. Today we will cover lecture number 23 of Mechanics of Material 2, and this is about theory of column. We have just very little introduction of this in this lecture. Definitions: column, vertical members loaded axially with compressive loading. So if there is a vertical column loaded axially, is called as column. Buckling, sudden deflection, literally like this, or sideways of long and slender. It might be in this direction, out of screen. Due to compressive loading is called buckling. So this phenomena is called as buckling, and mostly buckling is a failure in columns. Critical load, the maximum axial load that a column can support when it is on the verge of buckling is called as critical load, PCR, critical load. So here, if this is the column that is straight, it is fixed here, a load P is applied here. Now it will, when it is at the verge of buckling, on the verge of buckling, a little load is applied. It will cause this column to become unstable, and this will move in this direction. To study the effect of this force, we have make here a spring having stiffness K. So in this diagram, B diagram, if you look at, this has been displaced and spring has been compressed, and this spring will exert a force, restoring force, that has been stored in this spring on this joint of column to push back it to its original position. So if a small deflection is made here due to this small angle theta, and total length is L, this is L by 2, half of the length. So if we make a diagram like this, if this is x-axis, this is y-axis, then this will be along x-axis, and obviously this, if you draw this, this is member, this member, and this is force. So this force is P tan of theta. By looking at this, you can find out that if this is P, if this straight is P, then this will obviously be tan of theta. Similarly here, so 2 will be there, and we know F is equal to K into delta from spring, mass spring system. We know this, F is equal to K delta, and Px, that is this force, one force, it is equal to P tan of theta, this long x-axis. If theta is small, then delta will become delta, this is this one, this distance, and make another triangle for displacement. This is L by 2, this is angle theta. So for small angle approximation, L is equal to r theta. So from there you will get delta is equal to L by 2 into theta. So that is the theta is equal to delta is equal to theta into L by 2, and since theta is small, then tan theta will be equal to theta. When you put value here, Px will be P theta, and restoring force will become, when you put value of delta here, F is equal to K into theta into L by 2, and displacement force will be 2, one bottom, one top. So but both are in same direction, x-axis, so that will be disturbing force will be 2px. If restoring force of spring is equal to disturbing force, this is disturbing force, if these are equal, or if this is greater than, that is the scenario, put the value here, K theta L by 2 greater than 2 P theta, theta will be cancelled out, P will be less than KL by 4, and it is in stable equilibrium, because we have considered this restoring force. This force is greater than disturbing, so if this is dominating, system is stable, and if opposite is there, P is greater than KL over 4, then it will be unstable, and if P is equal to KL over 4, then it is in neutral equilibrium, and this load will be called as P critical load. So at this load, column is just at the verge of buckling. So now one more derivation, very simple. Ideal column with pin supports. Ideal column, it is homogeneous linear elastic material, and it is perfectly straight before loading. So these are the assumption for ideal column. If displacement, if we denote displacement with the mu, like here, and from previous knowledge we know ei d square mu or dx square is equal to m. Previously we have used for deflection y, so ei d square y or dx square is equal to m. So instead of y, we are using mu. So from here m and both are in positive direction. So this is mu displacement from this straight line to here where the load is applied at this section. So from this section m will be minus p mu. When you put value here, ei d square mu over dx square is equal to minus p mu. When p take here and divide by ei, so the equation will be d square mu over dx square plus p over ei into mu is equal to 0. This is homogeneous. It is homogeneous because it is 0 here. Second part, because differential has square. Linear because the variable has only 1 degree. It is linear. V mu has 1 degree. Equation with constant coefficient. These are constant. This is constant and here it is constant. So homogeneous second order linear differential equation with constant coefficient. And its solution from mathematics, you will gain mu is equal to c1 into sin theta into square root of p over ei x plus c2 cos theta into p over ei square root into x. That is the solution. So if you apply the boundary condition, that is deflection is 0 at x is equal to 0 because it is at fixed it is at sports and there is no deflection at that, no buckling at this. So see, when you put in this equation, it is 0, c and c2 value of c2 will be 0. This 0 becomes 1 and overall value will be c2 here, and here it is 0, so c2 will be 0. And another boundary condition is mu is equal to 0 at s equal to l. So put in this mu 0 at s is equal to l. So since this has become 0, so there is no need to take this. We are just proceeding with this term that is remaining, and this will give us c1 sine into p over ei square root into l is equal to 0. C1 should be 0, and that is trivial solution, means column should be straight. So we should move with this term. So sine into p over ei square root into l is equal to 0. So for 0 or taking sine inverse of 0, it should be in n pi and n from 1 to 3. So this will give this result, and overall result will be p is equal to n square pi square ei over l square. The smallest value of p will be at when n is equal to 1, and at that it will be critical. P critical will be pi square ei over l square, and it is also called as Euler load. This critical load also called as critical load when n is equal to 1. In the case of column, mu is equal to c1 into sine pi x over l. C1 represents the maximum deflection Vmax which occur at the midpoint of the column. C1 is about deflection. If I is equal to a r square from radius of gyration, here is crossing area, put I here, it will be p critical pi square e into a r square or l square. So take this a here, p critical over a, that will become stress, and remaining thing is pi square e over, take this r square below of this, so it will be l over r square, and this is called l over r is called as slenderness ratio. So we have shown this term in the term of slenderness ratio, and take our smallest radius of gyration by using smallest I. So r can be obtained from here by using smallest I. So sigma critical will be equal to pi square e over into l over r whole square. So that is critical stress. Thank you very much.